Hi everybody, welcome to part 1 of the demonstration for the NIMS Step Block in Machining 220. This is a very much awaited demonstration video, as this is a pretty complex and challenging project. Here's the print, and you can see that there are quite a few different dimensions on here, including quite a few different geometric dimensioning and tolerancing controls. It can seem kind of impenetrable at first. I mean, where do you even start, right? How do you get from raw stock to this finished product? I mean, what's the first step that you take? So this demonstration is going to lay out our recommended steps that you take in order to manufacture this part. It's not the only way to do it, but it is a way to do it which will result in a good part every single time. As with all of the projects in Machining 220 and beyond, we don't give you a project planning worksheet, but we do give you a general procedure which basically gives you all of the information that you need in order to manufacture the part. It gives you a sort of general guideline for the steps that you ought to take, the kinds of tools that you should be using. It even gives you this step-by-step, three-dimensional representation of the part at different stages. But it's on you to actually digest all of this information and then put it into a proper project planning worksheet format. That includes all of the steps that you take, all of the dimensions that you cut to, all of the tools that you use for each individual step. There are going to be many more steps on the project planning worksheet than you see on this general procedure. But this document definitely gives you a great head start on completing that project plan. So the first step in this project, as well as with any job that you do on a manual milling machine, is that you need to check the tram of the head. At the very least, you have to check it, and very likely you will need to adjust it so that the head is perfectly perpendicular to the table. Now, I've shown you how to do this before, and so I'm just going to kind of run through it. If you're looking for more detailed information, go back and look at demonstration number 1 of the angle plate project, where I go really in depth into tramming a head, how you do it, and what kinds of effects it has on the finished product if you don't tram it in properly. So I'm going to make sure that this is really nice and clean. Grab my tramming plate, make sure that the bottoms of the pins are clean. Set that down, making sure that it's, none of the pins are sitting in the T-slots. Okay, so that's kind of more or less in position there. Let's bring this down a little bit closer, give ourselves a final position. Okay, let's see, are we centered? Yeah, we're pretty well centered there. Okay, about 1/4 inch or so off of the rim. And the pointer there is at about 12-15 degrees. Not too much so that we mess around with the accuracy of the measurement, but just enough so that we don't bind on the bottom of the body of the indicator there. Okay, I'm going to bring this down with the quill just until we get up to that, approximately that vertical position, and then lock the quill down. Okay, now I'm actually going to come over here to the other side and zero it over here, and I'm going to check the nod. I always check the nod first. So I always zero in this position back here, and then I come out to the front, and it looks like we're still 0. Okay, so we were already 0 in this direction, so that's a freebie, and I don't need to do anything there. Let's try this position. Actually, I'm going to go ahead and zero it here, and then you'll be able to see it better over on this side. So now we're adjusting the tilt. Okay, so it looks like I'm about 1.5 thousandths out. So let me go ahead and loosen the 4 bolts on the front of the head. Okay. Let's see if we're still at 0 here. We are. Okay, so this is going in the positive direction, the clockwise direction. So let's see what that means here. So if I push it up, it goes in the clockwise direction, right? So that means that the plunger is being depressed, or it's being pushed more on this side of the plate than on this side of the plate, right? Because it's more in the clockwise direction over here. So that means that the indicating plane is tipped this way, right? Tipped further to the right. And that means that the head of the mill is off at this angle, right? It's the top of the head is tipping towards the right, okay? And so we need to bring it back this way, tilt the top of the head to the left, in order to get this to read 0 on both the left and the right sides. So let me go ahead and turn the adjustment screw. Oh, wrong way. Okay, so you can see that it jumped a little bit there. Let's go back over here and see what that did to our measurement. Remember that there's a little bit of looseness in the adjustment mechanism, so if you see a big jump like that, make sure that you go and recheck your 0. Yeah, so it made a huge jump, but actually now both sides are reading 0. Okay, so that's because the head, for the tilt of the head, it's like there are two round register fits that fit together, right? And so when you're moving the head left and right, you're moving one of those diameters inside of the other, but it's not a perfect fit, right? So they're not always concentric to each other, right? So depending on the way that you load the screw that actually rotates the head, you can sort of move the diameter around inside of its mating fit, okay? And so that's why we get this sort of movement that doesn't behave completely linearly the way that we would expect it if we were just rotating about a known axis. Hope that makes sense. But so here we came out 0. Okay, so I'm going to go ahead and snug all these bolts back down, okay, and then recheck. Adjust my 0, come back over here, and yeah, we're still definitely within a half of a thousandths there, so I'm going to tighten the rest of the way and do a final check. Okay, 0, and very nearly 0. Okay, I'm going to go ahead and check the nod again. 0 it out here. Perfect. What does it say in the front? Yeah, about 1/4 of a thousandths. So that's perfect. Now, one thing you might want to go ahead and do is just pull the indicator back off and then go back into your 0 and just give it another quick rotation and check that you really are 0, okay? Because sometimes what happens is that you bottom out the indicator because you've over-traveled it, or you're actually touching here on the bottom of the body, right? And so the reason why you're getting no movement on the indicator is because you're out of movement, right? It's not registering any movement. So you really need to make sure that you're 0 because you're actually aligned and not just because you're committing some kind of a fatal error here. But this looks really good. Okay. Next is the vise. And we should make sure that this is also very, very, very clean. You know, your hands are really the best indicators. Okay, I'm going to go ahead and remove this for just a moment. Okay, nice and careful. Just like that, right about in the center of the table. Okay, I use my fingers to line up the inside of the slots with the inside of the T-slots right here. And that gets it pretty close just off the bat. The bolts and T-nuts, go ahead and position those in the slots. And now I'm going to go ahead and get this one, I don't know, just really, really, really lightly snug, okay? Really not very tight at all. But on the other side, I'm actually going to get this one down pretty good and tight, maybe half tight or something like that. Okay, what I want to do is create a pivot point, right? We do this all the time, where if we're going to be making adjustments, we want something to move along a very, very predictable path, right? And so we have a pivot point over here, and then we can, any kind of adjustment that we make is going to be swiveling around that pivot point instead of just sort of loosely floating around on the table. Okay, now I'm going to put it into low gear so that the head doesn't move around too much. Remember, we're still interested in maintaining like a 12-15 degree angle, but now it's going to be 12 to 15 degrees from the vertical position, right? Okay, so it's always relative to the orientation of the work surface, not oriented relative to the machine or oriented relative to the indicator or anything like that. I mean, the position of the body, orientation of the body doesn't matter, but the angle of this indicator tip to the work surface definitely does. Okay, I'm going to go ahead and move the indicator over to this side, or rather move the table over to this side. Okay, feed in on my y-axis until I get to my 0. Okay, and then I'm going to feed the table to the left. And you can see that we're not moving very much at all, okay? So just kind of getting it close by, using my fingers to line it up with the slots on the table, did a pretty good job here. Okay, so we're about, let's see, 5,000, 6, 7 thousandths of an inch clockwise, okay? So that means that this back jaw here, the fixed jaw, is at this angle, okay? And so we need to bump it back to, parallel with the table in order to get this to read 0. And so that means that we need to smack the vise on this side, okay? And just like when adjusting the nod, right, I've got two measurements, both of which are on this side of a common pivot point, okay? And so if I zeroed it out here, I'm basically just going to move it until it touches the 0 over here as well. Then go back and reset my 0 here, come over here, adjust, come over here, re-zero, come over here, adjust, and you just keep getting closer and closer every time. It's a good strategy to use. It results in good alignment every single time as long as you follow the procedure. Yeah, we're only like 1/1000ths out now, okay? I'm going to go ahead and re-zero this, okay, and then go back to the first side. Yeah, so it's telling me 2/1000ths, no, 1/1000ths, 2 graduations. Okay, so I'm going to go ahead and hit it the same way again, just until it bumps up against the 0. Okay, let's go double check. Yeah, I didn't really see any movement, but let's make sure. Okay, 0. Yeah, I mean, there's no movement. Okay, so I'm going to get these almost tight. Okay, and then go recheck. Doesn't matter which side I start from now, okay, because everything's equally tight. Just want to measure from side to side. Oh yeah, that's perfect. It dips a little bit right here in the center, but of course that's to be expected because this vise jaw is probably slightly worn in the center simply from seeing so much use right in that area. Okay, one final check. Okay, pretty much perfect. Okay, time to remove the indicator and indicall, and it's time to start talking about squaring up the block. Now, the stock that we selected is this mild steel stock, which is 1.5 inches by 2 inches, and then we cut it off to 2 5/8 of an inch on the bandsaw. Now, the reason that we selected that size stock is because we can tell from the print what the overall width, height, and depth dimensions are, okay? So this right here is the largest width dimension, that 2 inches 500 thousandths. This right here is the largest height dimension, so that's 1 inch 375. And then the 1 inch 875 right here is the largest depth dimension. And so this dimension is going to come in from the 2 inch stock dimension. This dimension is going to come from the 1.5 inch stock dimension. And then the 2 inches 500 is going to come from the 2 5/8 of an inch bandsaw cut dimension. But when we're roughing out all these dimensions, remember we're going to be following the squaring up a block procedure so that we can remove all of this material and get all of the surfaces square, meaning mutually parallel and perpendicular to one another. And we're not going to rough the dimensions down all the way to these final sizes. Remember, we always leave something like 30 thousandths of an inch or so on these dimensions so that we can go in and finish all of the surfaces after we've roughed everything out, right? We really want to remove all of the bulk material that we can to get this down to a general shape and allow the material to stress relieve, and then go in and finish everything to all the precision dimensions and orientation controls that we have for the geometric dimensioning and tolerancing. If we were to finish these surfaces before completely roughing everything out, then if the material stress relieved and deformed a little bit, then we wouldn't have any more material to correct for those errors. So let's rough this out to 2 inches 530. Let's rough this out to 1 inch 405. And then let's rough this out to 1 inch 905. I'll put those in parentheses because those are just reference dimensions that we use for roughing out, okay? But those are not the actual dimensions that we're going to care about for final inspection. So I mentioned the squaring up a block procedure, okay? And if you've forgotten what this is, remember that we have a whole detailed procedure for this entire thing, this process called squaring up a block, okay? So this procedure really requires that we set up and machine each one of the surfaces, 6 surfaces on a rectangular prism or more or less cube-like shape, okay? 6 surfaces in a very particular order, okay? So we actually have to label the surfaces sequentially, 1, 2, 3, 4, 5, 6. If you're going to reference this detailed procedure for squaring up a block, remember that it's based off of the size dimensions for the angle plate project. So the stock sizes and the sizes that you're going to rough everything down to are actually different. So our stock actually looks a little bit more like this. Something more like that, right? It's a little bit longer there. And so this is that 2 5/8 of an inch bandsaw cut, and then we have 2 inch stock and 1 1/2 inch stock. So this big broad surface right here is going to be side number 1. This is going to be side number 2. This is going to be side number 3, and this is going to be side number 4. Let's call this side number 5 and then side number 6, okay? And that's the sequence. So part goes down into the vise, side number 1 facing up, we mill that flat just to clean it up. Then side number 1 goes up against the fixed jaw, and side number 2 is facing up. We have a pin between side number 4 and the vise just so that we bias towards side number 1, make sure that that's straight up and down. Side number 2 perpendicular to side number 1. Then we flip it 180 degrees, okay? So side number 3 is facing up, side number 1 still against the fixed jaw, side number 2 down on the parallels. We still have a pin back there, and we machine side number 3 down. And we actually do it to a specific size now, right? We're going to machine that down to 1 inch 905, okay? Then we have 3 good surfaces, okay? So side number 1 on the parallels, sides number 2 and 3 on the vise jaws, machine side 4, perpendicular to these 2 sides, parallel to side number 1, and we're also trying to achieve a dimension, which is 1 inch 405. Okay, now we hang side 5 out of the vise, take an end mill and mill side 5 just to clean it up. Then side number 5 goes down on the parallels, sandwich sides 1 and 4 in the vise jaws, and then machine side 6 parallel to 5 and perpendicular to the other 4. We're also trying to achieve a particular size dimension, the last one, which is 2 inches 530. Make sense? Let's go do it. Okay, you've seen me do this before. If you want more detailed information on how to actually go about performing this task, you can watch demonstration number 2 of the angle plate project, in which I go very deep into this whole procedure, okay? I'm just going to kind of whiz-bang through this because, I don't want to waste too much time on it. Okay, octamill goes in. Okay, going to grab some parallels, just make sure that they're big enough so that I can fit my dial caliper down in there, but small enough so that I get a maximum purchase on the actual part. Okay, so that goes down on the parallels like so. Okay, bring the quill down just until the tool touches the top surface. Lock the quill down. Back the knee off. Go back up to my 0 position. Okay, and then I'm going to take, let's just say, 20 thousandths. Go ahead and take the part out of the vise. It cleaned up everywhere, so that's done. And relabel. Okay, part is nice and clean, and we put that on top of the parallels, like so. Okay, now we need a pin to go in there. So pin goes between side number 4 and the movable jaw, just like that. Side number 2 is facing up. Good vise pressure. Don't want this thing flying out. Okay, my knee is at 0 right now. I'm going to bring the tool down till it just touches the surface, right there. Very carefully. Lock the quill, back this off, 1 revolution. Back off the part, up to where my 0 was, plus another 20 thousandths. Okay, and this cut I'm actually just going to take, I can actually finish this all in one go, so I'm just going to position the cutter directly over the center. Okay, part comes out. Okay, so that was side number 2. Okay, part is clean. All right, side number 1 is still up against the fixed jaw. Side number 2 is now down on the parallels, like so. Okay, and we still need a pin between side number 4 and the movable jaw. Okay, so right there. Good vise pressure. And I'm actually going to hammer this down onto the parallels, because I want to make sure that side number 3 is going to be parallel to side number 2. Okay, right there. Bring the quill down till it just touches the material. Lock that down. 0 the knee. Back it off. Come back up to my 0, plus 20 thousandths just to clean up. Okay, so that's telling me 1 inch 951. So 1 inch 951, and we're trying to get down to 1 inch 905. 1 inch 951 minus 1 inch 905 gets you 46 thousandths of an inch. So I might as well just take that all in one go. The maximum cut for this tool is about 70 thousandths. But only when you're fully clamped, okay? When you've got the pin in there, it's maybe like 30 to 50 thousandths. So 46 is inside that range, but it's kind of at the top of the range. Okay, another 46 thousandths. 10, 20, 30, 40, and 6. Okay, so that was side number 3. Where did we end up on here? It says, yeah, 1 inch 905, so pretty much perfect. Back this off a little ways. So now we have 3 milled surfaces, okay? And so now we can go straight down onto the parallels with side number 1, no pin needed, okay? And go ahead and tighten the jaws down. Hammer this down. Make sure that the parallels don't move. Good. Okay, come down and touch off on the surface. Just like that. 0 the knee. Okay, back it off 1 revolution. Come off the part. Back into my 0 plus 20 thousandths. So that says 1 inch 452. So we're at 1 inch 452, and we want to get it down to 1 inch 405. So 1 inch 452 minus 1 inch 405 gets us 47 thousandths. Again, I'll just take that all in one go. Go another 47 thousandths. 10, 20, 30, 40, and 7. That was side 4. So what did we end up getting there? Yep, that's 1 inch 405, pretty much on the money. Install the parts, so side number 1 is down on the parallels, and side number 5 is hanging out from the vise jaws just a bit. Just enough, not too much. Lock down the vise. I'm going to move this away just a little bit so that I can get access to the part with the hammer without knocking off any bits from the head of the mill. Okay, neither of the parallels are moving. And you know, I forgot to put our table protectors back on here, so let me go ahead and clean this off and then reinstall those. Beautiful. Okay, it's time to remove the octamill. Back the drawbar off. Pop it loose. So time to install a high-speed steel end mill. And this one has a 1 1/8 of an inch diameter. The flute length is about 1 3/4 inches. And the shank is 3/4 of an inch. So I'm going to grab a 3/4 inch R8 collet. Make sure that's nice and clean. So that goes into the spindle first. Where is that pesky key? There it is. Okay, pull that up into the spindle just a little bit. Okay, and then the end mill goes in. Draw the collet up a little bit. Lock it down a little bit, and then tighten it the rest of the way. Okay, so we really want to keep the quill extension to a minimum, just so that we increase the rigidity of this cut. So I'm going to lift the knee up, just so that I know that I'm cutting the entire surface with the flutes of the end mill. The surface is significantly smaller, or shorter, let's say, than the length of the flutes. So it's pretty easy to get that. So that looks perfect. This goes into low gear. Start the spindle. Okay, adjust the speed. All right, move the cutter so it's close to the end of the part. And then feed it in really nice and slow until you just pull a little bit of a chip. Just want to touch off here. Okay, right there. I'm going to call that 0 on the digital readout on the x-axis. Okay, pull that off the part. I'll go in, let's say 20 thousandths of an inch and take a cleanup cut. Lock the table down and then feed it by hand with lots of coolant. All right, it looks like we cleaned up everywhere on that surface, and that's all we were trying to accomplish, so we're done. Okay, so that was side number 5. So side number 5 goes down on the parallels now, just like that. Tighten it down. Back this off a little bit, hammer it down. Make sure that the parallels don't move, good. Okay, and we do it all again. Okay, I'm on center with the tool here because I can finish this whole surface in one go. All right, touch the top, lock it down, 0 the knee, back it off 1 rev, off the part, go back into my 0, and then 20 thousandths is a good cleanup. Okay, I'm back in high gear now. Adjust the speed and take the cut. It's telling me 2 inches 563. So we're looking for 2 inches 530. So 2 inches 563 minus 2 inches 530. 33 thousandths, all in one go. All right, 33 thousandths, so 10, 20, 30, and 3. So that was side 6. And what did I get for a measurement in this direction? Yeah, 2 inches 531, so super close. All right, folks, I hereby declare this part squared up and roughed out. This is where the fun really begins. This is where we start doing stuff that we haven't done before. And the first one of those things is putting in the steps using a roughing end mill. Okay, according to the print, we've got 2 little steps right here that go through the 2.5 by 1 3/8 surface. The first one is 750 thousandths from the bottom. The second one is 1 inch 125 from the bottom. Okay, and then this dimension right here is 1 inch 500 for that first step, and then this dimension from the left side is 1 inch for that second step. It says 2 times right there because there's actually a slot that goes through the part. You can see it in the top view and on the right side view. That slot goes all the way through the part, and it actually kind of bisects this top surface here, splitting it into 2 little tabs or wings, whatever you want to call them. And so that's why this says 2 times, because actually there are 2 different dimensions here, 2 1-inch dimensions, because they're technically 2 separate surfaces. It's important to notice where these dimensions are being called out from, okay? So the heights of the steps are being called out from the bottom of the part, datum A, not the top, right? So they're not depths, they're actually heights. And then the widths of these steps are actually being given as a distance from datum C, the left side of the part, okay? So not from the right side of the part. So actually you're not given the width of the step itself, you're given the width of the material on the side of the step. All right, in order to form a strategy for how we're going to remove this material, I'm going to go ahead and draw all of this up on a whiteboard, and then we can take a closer look at it. Okay, so this is basically what the part looks like, okay? And we have a few different dimensions here. Let me go ahead and draw those in. And the way that we're going to remove this material is in as few steps as absolutely possible. So let me go ahead and draw in the material which still remains to be removed. When we come in with the roughing end mill, okay, we're going to remove all of this material and then all of this material. So let me go ahead and draw that in. So this is the first to be removed. Okay, and then we're going to remove all this material. And the reason we have to take this in 2 cuts is simply because our end mill is not big enough to be able to take it all in one. If we could take it all in one, we would. And then we're going to take this third amount of material to get the second step. So 3 cuts is the minimum number of cuts that we can take in order to remove all of this material with this particular tool, okay? It's a 3/4 of an inch roughing end mill. We're using a roughing end mill because it's designed to be able to take full depth of cut. But the way that we're going to be touching off on the material and setting our reference positions is by touching off on the top of the part and by touching off on the right side of the part, okay? But remember that all of our dimensions are coming from the bottom of the part and from the left side of the part. So we need to do some calculations here to figure out exactly how far over we're going to go, right? So basically, we know what the overall dimension is, and we know what this dimension is, and so if we subtract this from this, then we can figure out what we're actually supposed to remove. That's the gist of it. The same goes for the heights, okay? So we know what this overall height is, and we know what the height of the step is, and so if we subtract this from this, then we can figure out what this is, right? The amount of material we're supposed to remove so that we're left over with this amount. Now, this is just a little bit further complicated because this is not actually what the part looks like right now, right? These are the final dimensions, but we are actually at our roughing dimensions. And we still want to leave some amount of material to remove off of the surfaces of the steps, because the roughing end mill is great for taking big, heavy, hogging cuts, but it doesn't leave a very good surface finish, okay? So we're still going to want to go in and finish all of those surfaces with a different type of end mill, a carbide end mill that we'll get into in another video. So we have to account for the extra material that we have on here to finish all of the outside surfaces, and we need to leave a little bit of material on all of the step surfaces so that we can go in and finish those later too. So in reality, the part looks like this right now. So we're 30 thousandths of an inch over size on all of the overall dimensions, which means that per side, we've got 15 thousandths of extra material. So all of the sides have an extra 15 thousandths, right? So if we have 15 thou here and 15 thou over here, that's 30 thousandths over size on the overall dimension. We're also going to want to leave about 15 thousandths of an inch on all of these surfaces, okay? So after we're done roughing out the steps, they're actually going to look something like this, where we have an extra 15 thousandths of material everywhere here as well, both on the sides and on the bottoms. So this distance from the left side of the part to this side of the step is not going to be 1 inch. It's going to be 1 inch plus 15 and plus 15. So it's actually going to end up being 1 inch and 30 thousandths. And the distance from the left side to the side of this step over here is not going to be 1.5 inches. It's going to be 1 inch 530 thousandths. Likewise, this height is not going to be 750 thousandths. It's going to be 750 plus 30, 780 thousandths. And then this dimension's not going to be 1 inch 125. It's going to be 1 inch 155. So let me go ahead and erase all of the irrelevant information now, and let's just look at what we've got for our roughing dimensions. Okay, so here we go. We've got 2 inches 530 thousandths roughed out width, 1 inch 405 thousandths roughed out height, and actually these numbers will differ potentially on your part, right? My part came out very, very close to our target roughing dimensions, but yours might be a little bit bigger, a little bit smaller. So just on the angle plate, you may have to compensate, right? So measure your part and then plug those numbers in here for the overall dimensions. Okay, so the heights of the steps are going to be 780 thousandths and 1 inch 155 thousandths. And the widths of the steps are going to be 1 inch 30 thousandths and 1 inch 530 thousandths. This area in red represents the material that's going to be removed. So as I said before, we know this distance and we know this distance, but we need to know this distance because our end mill is going to be right here. We're going to touch off on the top and move down and touch off on the right side and move over. Okay, so we need to know what this distance and this distance are. So this distance right here is going to be 2 inches 530 thousandths minus 1 inch 530 thousandths. So that's 1 inch. This distance right there, from here to here, is going to be 2 inches 530 thousandths minus 1 inch and 30 thousandths. So 1.5 inches. Okay. this distance right here is going to be 1 inch 405 thousandths minus 780 thousandths, so 625 thousandths. And then this distance here is going to be 1 inch 405 minus 1 inch 155, 250 thousandths. Now, it's important to remember that these dimensions are what we're going to use to position the cutter, but actually what we really care about are these dimensions here, okay? It doesn't matter how far over you go, right? What we really care about is that you have this distance from the left side of the part, for example. So the actual distance that you need to move here is going to depend on what size your part actually ended up, how heavy you touch off with the end mill, because the end mill is going to be a dynamic touch off, and so you're going to remove a little bit of material when you touch off on the surface. So at the end of the day, this is only a guide for us, okay? We really care about nailing these dimensions here. I hope that that makes sense. If it hasn't quite sunk in yet, hopefully it will. As soon as we go back to the machine, you actually see me do it. Okay, folks, so the first step here is that we need to fixture the part in the vise. And we're going to need to make sure that we select the correct size parallels so that we have enough of the material exposed so that we can actually get down deep enough to mill out those slots, or the steps. I've got a parallel set right here. And remember that the standard height of these vise jaws is 1 3/4 of an inch. And remember that the height of the bottom step here is 780 thousandths of an inch. Actually, that's the roughing dimension, right? But that's what we're going to cut this to. So the maximum amount of material that we can really hold on to is about 3/4 of an inch, okay? Because these parallels come in nominal sizes in 1/8 of an inch increments. So 1 3/4 of an inch minus 3/4 of an inch means that we need to grab some 1 inch parallels. Okay, so the 1 inch parallels go down. Part is clean. Let's see how that fits. Okay. So we have 11/16 of an inch exposed right now. And remember that with our end mill, we're going to go down 5/8 of an inch for this first step. Okay. So we have about a 1/16 of an inch to spare. That's pretty close, but you know, clearance is clearance. Okay, I'm going to tighten that down. Move this out of the way just a little bit and hit it with the hammer just to seat it. Okay, none of the parallels are moving. Good. So this is the roughing end mill, sometimes affectionately known as a corncob cutter, just because of the way that it appears, right? So a few differences here between this one and a regular end mill. The helix angle is a little bit less aggressive, but obviously the big difference here is these scalloped edges here, the scalloped cutting edges. Just like a serrated bread knife, the more convolutions you have in this cutting edge, the more surface area there is in the actual cutting edge itself, okay? And so that's why these can take such enormous heavy hogging cuts. It also helps to break up the chips, which otherwise would be very, very large because of how much material we're removing, into smaller chunks, smaller, more manageable chunks. That helps to evacuate the chips from the flutes and from the cutting area. Because of the way that it breaks up the cut, also, this is much less prone to chattering. So there are a number of great reasons to use this tool. The only real downside here is that it doesn't leave a very good finish. Now, we could hold this in just a regular old collet, right? This R8 collet's got a 3/4 inch shank. We could do something just like this, like we've done with the other end mills in the past. One big benefit of this tool holding device is that it reduces the stick out of the actual tool dramatically, okay, from the end of the spindle nose here, right? So when we shorten up that stick out, we reduce chatter and we reduce deflection, both of which we really care about since we're taking such a big, deep, heavy cut. But a big downside to this tool holding device is that friction's the only thing holding the tool in there. So if there's an upward or downward force on the tool that's strong enough to overcome friction, then this thing can come right out. And in fact, just exactly such a force exists. Okay, think about this for a moment. The flutes on the end mill have a helix in them, okay? So they're almost like a screw thread. And as you're taking a cut, The cutting action is actually drawing the tool out of the collet. Or vice versa, it's actually drawing the part up out of the vise. Now, normally this force just isn't strong enough to significantly alter the axial position of the cutter or to pull the part up out of the vise, okay? But when we're taking a really big, deep cut like this, it definitely can have an effect. So basically, after you've set all of your positions and you go to take a cut, let's say the height of the step will be bigger on one side than on the other side, because as you're taking a cut, the cutter's coming out of the collet. This has happened to students many, many times on this project. So we actually don't recommend that you use a collet. There's another type of tool holding device that's very, very commonly used with end mills, and that's an end mill holder, okay, designed for this very purpose. Sometimes called a Weldon holder because of the company which first started manufacturing these to hold the end mills that they were manufacturing. This is really nothing more than just a very precise bore with an R8 taper on the other end of it and a set screw. So if you've ever wondered why there's a little flat on the shank of most end mills, it's because they're designed to be held in this type of holder with a set screw. So what I usually do to install these is just remove the set screw, stick the tool up into the bore, okay, line up the flat with the set screw position, and then I just dog down the set screw. Tighten it down with an Allen wrench, like so, and Bob's your mother's brother. So the set screw is a positive locking device, which ensures that the end mill can't retract from the tool holder because there's mechanical interference there. But as soon as I install this, you'll see what the downside to this tool holder is, right? You've got this much more stick out from the end of the spindle nose, okay? So this is much more likely to chatter, okay? And so what we might have to end up doing is play around with the speed in order to get this thing to quiet down. Okay, I'm gonna go ahead and tighten this down. Okay, first thing I wanna do is come and touch off on the top of the part. Just gonna do a quick static touch off here. Just bump it against the surface, be careful. Okay, zero out the knee, back it off one revolution, and then come back over to the right side of the part, and then go back up to where my zero was. Now, according to the calculations that we did on the whiteboard, we're going to have to bring the part up 5/8 of an inch, 0.625. We're going to adjust that distance using the knee, okay? Even though there's a digital readout on the quill, it's not really that accurate, okay? So it's better to use the knee for this. And to make this easy, let's just remember that the dial on the knee goes from 0 to 90 and then back to 0, okay? So it's 100,000ths of an inch per revolution. So if we're trying to go 625 thousandths, that's 6 full revolutions plus 25. Okay, so I'll do that now. 1, 2, 3, 4, 5, 6, and then another 25 thousandths of an inch right there. Okay, to adjust the left to right position, I first need to touch off on the side of the part over here, and I'm going to use a dynamic touch off for that. So go ahead and flip this to low speed, turn it on, adjust the speed. Okay, and then I'm going to slowly feed into the part until I just take a little chip. So this is pretty, familiar to us at this point. Okay, right there. Okay, pull completely off of the part, and then go ahead and zero out the x-axis on the digital readout. According to our whiteboard calculations, we're going to go 1 inch from the right side of the part. Okay, but we can't do that all in one cut because this end mill is only 3/4 of an inch in diameter. Okay, so let's split it up into 2 cuts. 2 cuts of 1/2 inch. So go ahead and move the digital readout so that it reads 500 thousandths. Okay, right there. And then I'm going to feed the table towards me by hand along the y-axis. Okay? Now, a couple of things here. It's important that you conventional mill rather than climb mill, okay? Climb milling is going to cause all kinds of problems here because this is such a big, heavy cut. So if we're cutting on the right side of the part, to conventional mill, we're going to start with the part away from us and move it towards us. The other thing about this setup is, some people may wonder why we have the part in this orientation, right? Because if we have it in this orientation, then we have to feed by hand along the y-axis. Why don't we orient it 90 degrees and then we could feed it along the x-axis using the power feed? That's a very valid point, but there is a reason that we're doing it this way, okay? We're going to be taking a very, very heavy cut, and there are going to be a lot of cutting forces involved. And so we are feeding against the fixed jaw because that way there is a hard mechanical stop to absorb all of those forces. If we were to orient the part 90 degrees, there would be no physical stop there to absorb the forces. The only thing counteracting the cutting forces would be the friction between the two vise jaws, okay? But actually, if the forces are big enough, then we can actually start cocking the part out of the vise jaws like this, and then we're again going to have problems because we're going to lose the position of the part, and we're going to cut a feature that isn't square, and it's going to have a difference in size from one side to the other. So this really is the best way to do it. We are going to use a lot of coolant, okay, because again, this is a very heavy cut. There are going to be a lot of forces involved and a lot of heat that's generated. All right, without further ado, let's do it. Okay, and it's really nice. It's not chattering at all right now, although you'll see in just a moment, I'll actually show you that you can get it to chatter. I'm feeding, it's about 1 or 2 inches per minute, not very fast, okay? But watch what happens when I slow down. Okay, now I'm slowing down and now it's really chattering, okay? But as soon as I start feeding it a little bit heavier, it stops chattering, okay? So when you're feeding with a heavy enough feed rate, okay, then actually you are loading the cutter in such a way that it's kind of absorbing vibration. So you really need a minimal amount of feed on this in order to get it to cut properly without chatter. Okay, we're at the end of the cut now. Okay, perfect. Back to the start of the cut. Okay, go ahead and unclamp the table lock on the x-axis and then move over to our final position of 1 inch. Right there. Let's take the cut. I'm putting, a considerable amount of force into getting this to move, all right? But it's not that much. I mean, it's going pretty freely. If it feels like you're trying to feed up against an immovable object, then it's probably because your cutter is too dull. Okay, very good. Now, in order to get to the height of the second step, all right, we could just move the part down from this position a certain distance, and that would get us there. But actually, I feel like it's easier just to touch off on the top of the part again. So I'm going to do that. Okay, I'm going to back this off, unlock the table, move over here on top of the part surface. Okay, come down with the quill right there. lock it down good and tight, okay? Then I'm going to back off 1 revolution so I don't drag the tool across the part surface over here, okay? Go back down to where my 0 is. So according to our calculations, we need to take a 250 thousandths deep cut to get to where the top of this second step is supposed to be. So again, basing that off of numbers of revolutions on the knee crank, okay, that's 1 rev, 100 thousandths, 2 revolutions, 200 thousandths, plus 50. Right there. Okay, now that we've got the depth set, okay, let's go ahead and move the end mill off of the part. According to our calculations, we need to move over 1.5 inches from the far right side of the part, okay? So again, we're just going to base this off of our digital readout, and this cut we can take all in one go. So let me go ahead and move over to 1.5 inches, 1.50, right there. Lock it down, turn it on, and take the cut. There we go. Let's just take a quick measurement just to make sure that we didn't flub this up too bad. Okay, so that came out to 1 inch and 25 or 1 inch 26 thousandths. Good. This came out to 1 inch 525 thousandths. Okay, so 5 thousandths short, but totally within our roughing tolerance there. Okay, the heights are going to be a little bit more difficult to get. So that says 778 thousandths. Great. And this says 1 inch 153 thousandths. Perfect. Only 2 or 3 thousandths short on our heights here. Okay, the next thing to talk about is the slot that goes through the center of the part. So in the right side view, we can see that the width of the slot is 875 thousandths, and the height of the slot from the bottom of the part is 1 inch. And as you'll remember from the lecture video for this project, this GD&T callout right here, this tolerance of position within 5 thousandths of an inch to datums A and B, datum A being the bottom of the part and datum B being the center plane constructed between these two surfaces, what that means is that the center plane of the slot is supposed to be coplanar with the center plane of the part. In layperson's terms, this means that the slot is supposed to be on center of the part. It's supposed to go right smack dab through the middle. So in order to cut this feature, we have to watch out for 3 separate things. One is that we need to figure out exactly how deep to cut the slot so that we get the correct height from the bottom. The second is that we need to machine the width of the slot so that we leave a little bit of extra room per side to finish up later on. And the third thing is that we need to find the center of the part so that we can just drive the end mill right through the center. The depth of the slot is a simple thing to achieve. Just like we did for the steps, we're going to add 30 thousandths of an inch to this dimension. So that's going to account for the 15 thousandths of extra material here on the bottom of the part, what's going to become our datum A. And it also accounts for the 15 thousandths of material that we want to leave on the bottom of the slot to finish later on. So keeping in mind that our overall height right now, the roughed out height of the part, is 1 inch 405 thousandths, the depth that we're going to go from the top of the part to the bottom of the slot when we're roughing is going to be 1 inch 405 minus 1 inch and 30 thousandths. So 1 inch 405 minus 1 inch and 30 thousandths. 375 thousandths of an inch, 3/8. Remember that this number might be slightly different for you because your part may have come out to a slightly different overall dimension when you were roughing. Okay, so that takes care of the depth of the slot. The width of the slot, we're actually going to rough this out to 750 thousandths of an inch. The reason for that is that our end mill has a diameter of 750 thousandths of an inch. So all we're going to do is set up the position of the end mill and just go right down the center of the slot, and that's naturally going to leave, let's see, so 875 minus 750 is 125 thousandths of an inch, an eighth of an inch. So that's going to leave 1/16th of an inch per side, about 60 thousandths per side to finish later on. Okay, easy enough. The last thing we need to do is find the center of the part.
Sorry folks, my audio cut out, so I'm going to have to do a voiceover for this next little section. I'm going to use an edge finder to find the center of the part. Remove the roughing end mill for the moment. Install the drill chuck. Lower the table. Install the edge finder. Lower the quill so the part is about halfway up the small diameter on the end of the edge finder. Start the spindle. The maximum speed is 1000 RPM. If you spin it faster than this, the tip of the edge finder may come flying off. Move the y-axis until the edge finder touches the surface and the tip of the edge finder just pops out. Zero the y-axis position on the digital readout. Then raise the quill. Now, there are basically two ways to find the center of the part. The first way is to measure the depth of the part with a micrometer and then move the table half of that measured distance plus half the diameter of the edge finder. That's a perfectly legitimate way of doing it, but there's a second, better way which requires fewer steps, and that's the way we're going to do it. So move over to the other side of the part. Lower the quill. Turn on the spindle. Slowly move in just until the edge finder pops out. Then raise the quill and turn off the spindle. Now the y-axis position on the digital readout reflects the distance between the two surfaces plus the diameter of the edge finder. And because we touched off on opposite sides of the edge finder, feeding in opposite directions, we do not need to account for the diameter of the edge finder in our calculations. It sort of cancels out. All we have to do to find center of the part is divide the y-axis position by 2 and then move the table back to that position. So 2 inches, 100 thousandths, let's say, divided by 2 is 1 inch and 50 thousandths of an inch. So move the table back to 1 inch and 50 thousandths, then lock the table back down. Now the spindle should be right over the center of the part in the y-axis direction. Okay, the edge finder comes out, followed by the drill chuck. Then the roughing end mill goes back in the spindle. Position the roughing end mill over top of the part. Lower the quill until the bottom of the end mill touches the top of the part. Lock the quill. Zero the dial on the knee crank. Back the knee off 1 revolution. Move the tool off the part. Raise the knee 1 revolution back to the 0 position. We're going to raise the knee an additional 375 thousandths of an inch. So that's 1 revolution, 2 revolutions, 3 revolutions, plus 75 thousandths. Start the spindle, adjust the speed, and take the cut straight through the center of the part. Make sure to use lots of coolant. Clean off the chips. There you go. Remove the roughing end mill. Remove the end mill holder.
So basically, this part is roughed out now. We typically put holes in right at the end after all of the flat planar surfaces have been finished. But we're actually going to go in and rough out this 750 thousandths diameter hole, because it's big enough and it's close enough to these surfaces that if we try to drill it out right at the end, it could actually cause some distortion, especially right here, where the wall thickness is really thin. So we're going to go in with a drill, which is the next nominal size in a 1/16th of an inch increment below this size right here. So this is 3/4 of an inch, or 12/16. So we'll go in with an 11/16 drill. So this is the 11/16 of an inch drill that we're going to use. It's a reduced shank drill, so it's got a 1/2 inch diameter shank, so it'll fit into a regular drill chuck. It's also got a split point, so we don't have to pilot drill before we go in with this drill, even though it's large enough that we technically should. When you grab one of these, make sure that the cutting edges are very, very sharp and that the split point goes all the way to the center of the drill. These drills are something that we actually sharpen in-house, and actually when we meet in person, I will show you how to sharpen these yourself using our Derek's drill sharpener. So if the person before you broke the drill or sharpened it but didn't do it properly, it's on you to fix it. And just because this has a split point on it doesn't mean that we don't need to go in with a center drill or a spot drill or something to give this some kind of a small mark to locate itself. Okay, so we're going to do like a number 3 or number 4 center drill first and then go in with this thing. Like all holes, this one has both a size and a position, okay? So we've only talked about what size we're going to machine this to. We also have to talk about where we're going to put it. So the final position of this hole is going to be 2 inches from the left side, otherwise known as datum C, and 500 thousandths from the front of the part, otherwise known as datum D. Just like with all of the other roughing features on this part, we have to keep in mind that we still have extra material on all of the surfaces on the part right now. So wherever we put this feature right now, once we go in and finish all of the outside surfaces, the position will have moved. And it will have moved a distance equal to however much we take off of these surfaces, which is going to be about 15 thousandths of an inch. We are leaving a little bit of material in the hole to come in and finish later. And because of the tool that we're going to use to finish the diameter, we can actually change the center position of the hole slightly. But even then, we would like for the hole to be as close to its final position as possible when we go in to finish it. So instead of pre-drilling this hole at 2 inches and 500 thousandths, we're going to add 15 thousandths of an inch to both of those dimensions so that when we take 15 thousandths off of both of these surfaces, the hole will be approximately where it's supposed to be. So 2 inches and 15 thousandths from datum C, the left side of the part, and 515 thousandths from the front of the part, or datum D, is where we're going to position the drill. So I've already got the drill chuck and the edge finder in the spindle, so let me go ahead and touch off on this surface and find our hole position. Okay, so I'm just going to position the edge finder in front of the front surface of the part. Okay, turn on the spindle, move it in, flip that around so you can see it better. Move it in just until it touches and then pops out right there. Okay, bring that up. So now I'm going to zero out the y-axis on the digital readout. I just touched off on the outside of this diameter. So if I want to get the center of the spindle over top of that surface, I need to move over half of the diameter of this surface right here, the cylinder on the end of the edge finder. So I know that this is 200 thousandths, so I've got to move over 100 thousandths. So 100 thousandths on the y-axis, right there. Zero out the digital readout again. And now I can move 515 thousandths of an inch. Right there. And I'm going to zero that out again. So now my zero position on Y is where my hole is supposed to be. Okay, I'm going to do the same thing in the x-axis. Right there. Bring the quill up. Zero out the x-axis. Move over 100 thousandths of an inch. Right there. Zero that out. And then move 2 inches and 15 thousandths. Right there. And then I'm going to zero that out as well. Lock the x-axis down, move back to my y-axis position, 0 on the y-axis. right there. Lock that down. And now I can go ahead and drill the hole. First is the center drill. Turn on the spindle. Okay, we're just going to kind of make a little spot right there. Perfect. It doesn't need to be very significant. Just a little punch mark, basically, so that our drill can locate. Before you actually remove any substantial amount of material, this is a good time to just double check roughly with a ruler to make sure that you're on the right location. So I'm supposed to be about 2 inches from this side, and it definitely looks like I am. And I'm supposed to be about 500 thousandths from this side. And it certainly does look like I am. Perfect. Okay, I'm going to have to lower the table considerably to get this thing in there. I think that's good enough. Let's see. Right there, perfect. Nice and tight on there. We really don't want the drill to spin in the drill chuck. Turn the spindle on, adjust the speed. Lots of coolant. Here we go. Cutting very nicely. I just back off a little bit on the quill whenever the drill, the chips from the drill get big enough that they are about as long as the flutes of the drill. Oh, here we go. Beautiful. One thing that I didn't mention, but which I should have, is that this hole is so close to this surface over here that actually we have to make sure that we use parallels that are not too wide, right? So like these 1/8 parallels are right on the borderline there where as you're drilling through, you might actually start cutting on the parallels. I mean, it just clears, okay? I mean, it's technically okay. And so you got to use at least the 1/8 parallels, right? And later on, when we actually go in to finish this, we're going to be even closer to that surface, right? So actually, these will no longer do. So then we go to the 1/32 parallels, the really, really thin parallels. But for roughing out, 1/8 is fine. But we have some other parallels in there that are bigger than 1/8 of an inch. Like these are the 1/4 inch thick parallels, okay? Those definitely would not work. And as soon as you busted through that hole with the drill, you'd start drilling on the inside of the parallel here. And actually, as you can see, quite a few people have done exactly that. So don't be that person. All right, folks, this part is all roughed out. And we're ready to start finishing operations. But that's it for this demonstration video. And in the next video, we will continue on and actually finish the outside surfaces. I'll see you then.